Mhm. Yeah, that's a great question as well. So the question is, how can we be certain that dark matter actually is affected by gravity in the same way as visible matter? Well, I think that the measurements that Stefan showed actually provide some hints at the answer. So in particular, Stefan showed a picture of a background galaxy being distorted in its shape by a foreground galaxy. And the reason it was distorted is mass that was in between the background galaxy and us within that foreground galaxy, and that mass was dark matter. So we at least know that dark matter creates gravity from a technique like that. The question of how do we know dark matter itself feels gravity? Well, these lensing measurements, if you do them on a lot of galaxies, they actually show you what the spatial distribution of the dark matter is. And you can say, okay, well, what is the distribution I'd expect if dark matter interacts by gravity? And comparing those two, you get good agreement. So that's, I think, just one example of how we can answer that question. There are a lot of other techniques that also give us traction. Okay, one more question, and then we should keep going. Okay, great. So a final piece to this story, and then we get to look at some more pictures, is something Stefan also alluded to, that the universe is expanding, and as it expands, it cools. So that's actually a pretty normal piece of physics. It turns out that most things, as they expand, they also cool. And you've probably seen that if you ever baked a cake and then take it out of the oven and you see it kind of expands a little and also gets cooler. But as the universe expands and cools, the temperature, which I'm showing on this red line here, is actually dropping as time moves forwards. So this little ball is representing where the universe is on this trajectory. And you'll see in the next couple slides, this ball will be sliding down, and that will give us a sense of what physics is important. And basically, when the temperature is high enough, the universe is ionized. So these electrons and protons are just running around, interacting very strongly with the light, creating pressure. And the light is basically stopping the regular matter from being compressed by gravity. Meanwhile, when the universe is neutral, that doesn't happen anymore. The electrons and protons have combined. They're not interacting strongly with the light, so the light is not able to provide pressure. So this transition point here in purple is actually a very important point. And this little purple ball, if you'll follow along with it, will actually give us a way to track when we reach that point. Okay, so now what I want to do is set up a toy problem. Basically say, if I had one lump of extra matter, extra photons or radiation, and extra dark matter, and I started it off at the center of my space, how does that evolve in time? And I'm just going to show you some plots that I made that actually describe exactly, at least in a theoretical framework. I can chat about more during the break, but that's a standard one. They describe exactly this evolution. So just how to read these plots. This Z is a redshift, 80,000 right now. Higher redshift actually corresponds to earlier time. So you'll see this redshift number going down. That means that time is actually going forward. So this is a very, very early time in the universe. Now, this legend is just going to reappear on every slide. The blue is the regular matter, the black is the dark matter, and the red is the radiation or light or photons. And it's hard to see them because they're all overlapping here. And that's just the initial condition that I set up. And by the way, this vertical axis is just the mass. So it's saying I just have some lump of all of this stuff right at the center. Again, our horizontal units are megaparsecs, or 30 times the width of our galaxy. And so I'd ask you to look for what happens around this 150 megaparsec scale, because that's the scale we're really interested in. But you'll be able to distinguish these curves more, I promise, as we move forward, because they'll separate. So at this very early time, the universe is ionized, and it'll remain ionized for a couple of graphs I show you. But now let's move to a later time. So later, a couple of things have happened. One is this dark matter is actually higher up than it used to be. That's because gravity is causing other dark matter to come in from outside and glom onto this dark matter at the center. So this dark matter at the center actually gets to grow. That's consistent with what I told you before, that gravity compresses and dark matter experiences only gravity. So it gets compressed, and therefore more of it ends up at one region. There's more dark matter mass over here now than there used to be. Meanwhile, something really interesting is going on over here. You see this blue and this red, the regular matter and the radiation are locked together, and they're moving outwards in this lump. So why is that going on? Well, the universe is ionized. That means that the regular matter is interacting very strongly with the light. And that means that whatever the light does, the regular matter has to follow. So that's why they're locked together. But now, why is the light doing what it's doing? Why is it moving outwards in this pulse? And the answer is because my initial condition, which I'll flash back to, here I set up extra light, extra radiation right at the center. Now that extra radiation means I had extra pressure right at the center. So it's like a very compressed balloon that I'm squeezing in my hands. Now when I let go, that balloon will expand. So here, as time goes on, the extra pressure actually causes the radiation to move outwards to greater distances from the center, and it carries the regular matter along with it. So now let's move the time arrow even later. You can see that this pulse has actually gone farther. Now it's at 100 megaparsecs. Meanwhile, the dark matter hasn't actually done anything interesting. It's just grown a bit, and you'll have to trust me because, you can't necessarily directly compare because the axes are changing a little, so you still get to see all the plot. But the dark matter has just grabbed a little bit more matter via gravity. It's never going to do anything interesting except very much at the end because it only interacts by one force. So there's only one direction it can change. So I hope that what I've said about the pressure still makes it comprehensible why this has moved out. Basically, there's still some extra pressure driving this, so it still wants to expand outwards in the quest for equilibrium. So now we're going to move so close to the universe becoming neutral. We're just right poised on that brink of the universe becoming neutral. And we see that the dark matter remains uninteresting, where the regular matter and the radiation have actually continued to move out in this pulse. And this pulse is now at about 120 megaparsecs, almost at this special scale that we're interested in understanding, but not quite. So now, thank you for your attention so far. We have something a little bit more fun, actually an animation of what I've just shown you. So enjoy the video. You can actually see, and I'll play it again, it's a little fast. You can see the regular matter and the regular matter and the light actually moving outwards in this pulse, and the dark matter is just growing, although that's a little hard to tell because this vertical scale is actually changing numerically just to make the plot visible. Okay, so now there's something crazy going on right at the end of the video. That's our next step. So the question is, what happens when the universe becomes neutral? We're sitting right here. What happens at this transition? Okay, well, first of all, the cosmic microwave background forms at this moment. Now, that's for reasons I've already described. Basically, prior to this, the light just gets scattered and can't get to us. And at this moment that the universe becomes neutral, we then get to see the light. So this is when the blueprint is formed. But something else happens too. Neutral means there's no more electrons. That means there's no more strong interaction between regular matter and light. And that means there's no more radiation pressure or light pressure on the regular matter. There's no way for the light to talk to the regular matter anymore. So what happens is that, and this is at a later time, quite a bit later actually, and we're sort of very much in the neutral region here. What happens is that the light actually keeps going because it's still moving. It doesn't care about the neutrality. In fact, it can go faster now that it doesn't have to push around all these pesky regular matter particles. But in the meantime, the regular matter in blue has actually frozen out at the scale of 150 megaparsecs, or 4,500 times the width of our galaxy. It actually just got dropped right there. It got dropped by the light, and an extra lump of it got deposited at this scale. Meanwhile, the dark matter kind of continues to do whatever it was doing, although you see there's a bit of dark matter out here now, and that's because the regular matter actually pulls the dark matter gravitationally onto it over here in this region. So we want to focus in on these two scales. Over here, we have extra regular matter and extra dark matter, so we have everything we need to form a galaxy. So in fact, you do get a galaxy right over here at the origin of our toy problem. But what you also get at this little bump here where you have extra dark matter and regular matter, and the extra regular matter is because of this freezing out of the pulse where the light just let it go right there. So right there, you also get a galaxy because there's just extra matter there. Now, this yellow line is showing this characteristic scale of about 150 megaparsecs, or 4,500 times the width of our universe. And it turns out that that is actually exactly this distance that we measure in galaxy clustering today. So as I said earlier, each sphere in this plot of galaxies has a characteristic radius, and it turns out this radius is about 150 megaparsecs. It's about 4,500 times the width of our galaxy. And the reason it happens is because of this physics that went on in the first 300,000 years of the universe's existence, when the radiation was strongly coupled to the regular matter and pushed it around. And then when the universe became neutral, the radiation said, see you later, and just dropped the regular matter at this characteristic distance. So I'd now like to pause for questions, and after that, we'll have a break. Sure.
So I was thinking about what you said earlier with space between the galaxies expanding and like a dark energy that's pulling it. I would think like we don't know a lot about dark energy, so how do we know that, like to a certain point, that dark energy, you know, all the galaxies drift apart, and then how do we know that dark energy is strong enough to eventually like take the planets apart and then take atoms apart and then take protons apart? Like, is there like a stopping point? How do we know that it's not eventually going to just like tear everything apart?
Yeah, so that's a great question as well. Very thoughtful and very worrisome, I think, as well. So, so the question was, how do we know that if dark energy is causing expansion of the universe on very large scales, that it won't eventually rip everything apart, even, you know, tearing apart the atoms that compose us? So the answer is that basically on smaller scales, like the scale of even a galaxy or even a system of galaxies that are orbiting each other, and certainly on the scale of protons and electrons, there are other forces that are much stronger and that go in the opposite direction. So in particular, if you have two galaxies orbiting each other, the gravitational force attracting them is much stronger than the dark energy that would be stretching the space in between them and trying to pull them apart. And things within our body are governed by electrical interactions, and those forces are also much stronger than dark energy would be, and they go in the opposite direction. So on the scales relevant to our body, dark energy can't compete at all. Great, so next question. Sure. Yeah, that's also a great question. So the question is there a reliable relationship between time and the value of the temperature of the universe? And by the latter, the temperature of the universe, the way to say it is that the temperature of the cosmic microwave background, because that's this background bath of radiation that permeates everything around us. And most of space is actually empty other than that. So if you're focused on more particular objects like the Earth, then of course, you know, there's no reliable relation. But if you're just focused on the temperature of otherwise empty space, then you're asking what is the temperature evolution of the cosmic microwave background? So the answer is actually no, there's not a completely reliable way of mapping the two, because we do know how the temperature of the universe changes as the universe expands. If you double the size of the universe, i.e. double the radius, then the temperature would drop by a factor of 2. But what we don't know is exactly what the expansion rate is as a function of time. So we can measure that pretty precisely, and we can extrapolate forward into the future. But since we don't actually understand what dark energy is, and different models of dark energy make different predictions, then into the future, there are different ways you can extrapolate that expansion rate, and therefore what the size of the universe is as a function of time, and therefore what the temperature is as a function of time. Okay, great. In the blue? Yeah, that's a great question as well. Very, very thoughtful. So the question is there still some pressure exerted by light on electrons and protons even once they get bound into atoms? And yeah, I actually have to think about this for a second for the best way to answer this. I think the answer is yes. So if you hit a hydrogen atom with a powerful enough burst of light, really what I mean by that is a high enough frequency burst of light. So, think about red light. Red light is lower frequency than blue light. And we're talking about something that actually goes up to the, I think, X-ray to be able to split hydrogen apart. But yes, if you hit hydrogen with an X-ray, then it will actually break apart. You will have ionized it. So I think, yeah, in that sense, atoms still do feel pressure from light. Of course, they can only absorb certain frequencies of light for reasons I'd be glad to talk with one-on-one. Okay, I think we have time for one more question, then we should close over there. Another great question. So how will the cooling of the universe affect global warming? Unfortunately, much as we might hope astronomy saves the day in this case, the answer is actually not at all. The Earth's atmosphere and the sun's light is basically what's controlling global warming, and we've put some chemicals in the atmosphere that kind of stop the light from being re-radiated as effectively, and the expansion of the universe is occurring only on much larger scales, as is the cooling. So today, the temperature of the Earth is not actually created by the cosmic microwave background. So cooling the cosmic microwave background down doesn't actually help you, but very, very hopeful prospect. Okay, well, I think that's all we have time for at the moment, but I will be around during the break. And after the break, please join me as Kate Alexander finishes up with a glimpse at the very, very first bit of the universe. Should I say how long the break is? Yeah, so the break will be 5 minutes also, so grab the cookies quickly. Thank you.
So how over time?
Thanks. Yeah, sure.
Hi, live stream viewers. We'll be taking a short break. We apologize for the brief interruption before. There is a new link to watch the second half of the live stream. We had it cut out during Zach's portion of the lecture, and we apologize for that. Please stay tuned in, and we'll get started in just 4 to 5 minutes. Thank you. ways, like we talked about at the beginning, and you can just leave them at the front table, and we'll collect those at the end. But for now, okay.
All right, welcome back, everybody. Hope you can all hear me just fine. We're going to have the third and final part of our lecture now, and we're actually going to end by going back to the very beginning of everything and explaining our current best understanding of where these small perturbations that Zach told us about came from in the beginning. So I'm going to attempt to answer three main questions throughout my talk. The first question is about this theory of inflation that you've heard mentioned a couple times now. I'm going to explain what this theory is and why we decided that we need this theory in the first place. I'm then going to talk about how we actually go about testing this theory. It's very nice to come up with a pretty idea of how the universe began, but since we're scientists, we want to actually have evidence to support this idea. And then I'm going to venture into the realm of cutting-edge experimental physics, and we're going to talk about some recent science results that may be the first direct observational evidence that inflation did happen. And this is going back to the theme we have been talking about and stressing this whole evening, which is that our understanding of the universe continues to advance with our technology. It's getting more precise all the time. And these are incredibly precise measurements that you have to make to try to understand the beginning of the universe. So our understanding will hopefully continue to grow as time goes on and technology continues to improve. So just to remind everyone where we were, in case you forgot while you were all getting cookies and so forth. When we look around today, we see a universe full of structure and order. We see galaxies which cluster together in these superstructures, and we know that most of these galaxies are made of dark matter, but there's also visible matter like stars and gas and human beings. And then Zach told us how these structures began as tiny perturbations in tiny hot and cold spot variations in the universe. And then these teeny tiny little differences grew over time and due to the interaction between gravity and pressure, and of course the universe expanding. So this is all a very observational based picture that we have put together. We look around at the universe we see today, which is about 14 billion years old. We see galaxies. If we look, the way we observe the universe is by looking at light. So if we look at light that is farther away, we're effectively looking back in time because it took that light a certain amount of time to travel the distance to us. We don't normally think about light taking time to travel because it's so fast. Light gets from the surface of the sun to Earth in about 8 minutes. But if you're looking at other galaxies and then you're looking further and further away, it does start to become significant. So if we look at light that's far enough away, we can see all the way back to the time when the first stars formed, which was about 200 million years after the beginning. And if we look even farther, we can see all the way back to the cosmic microwave background, which is this background radiation from when the universe became neutral that Zach explained so very well. And this is the oldest light that we can see directly in the universe. So this is all a very beautiful picture. We've heard about the small perturbations in the cosmic microwave background, how that grows into structure. That's all pretty well understood. However, when astronomers were developing this theory, they realized there were still some outstanding questions that they had that we wanted to explain. First question is, well, it's great to say that there are these small perturbations. It's great to show us how if you have an initial condition with slightly more matter in one place than another, you can see how it grows over time. But how did these perturbations form in the first place? And why are they the size that they are? Why is the universe not completely perfectly smooth? And then the other question, which is sort of, in a way, the flip side of this, is why does the universe look the same in every direction? Why is it that when we look at this spot on one end of the universe, remember this light took 14 billion years to get from this spot to Earth, and then we look at this spot on the other end of the universe, whose light also took 14 billion years to reach us. If you think about it, if light wanted to go from this spot to this spot, it would take 28 billion years. And the universe isn't that old. And if nothing can travel faster than the speed of light, why is it that this piece of the universe knew to be almost exactly the same temperature to less than 1/100% Why are they exactly the same temperature when they're so far apart they couldn't possibly have interacted with each other during using our current understanding? The last question is, how did the universe end up perfectly flat? This may seem like an odd question, but it's sort of, the analogy you can think of is back thousands of years ago, people looked around them at the Earth and looked out at the horizon and thought the world was flat because that's how it looked. But then when our technology got more advanced, we realized the world had to be round to explain observations we were making. And so you might imagine that the universe itself could also be curved space. And it turns out if you want the universe to be perfectly flat, you need the initial conditions to be just exactly right. You can't have too much stuff, you can't have too little stuff. It has to be pretty much perfect. And we can measure how flat the universe is today very precisely. And it turns out it's pretty much flat as far as we can tell. So we want to know, how did the universe start in this exactly perfect way so that all of these things are true, that we see exactly this spectrum of perturbations, we see the universe being the same on opposite ends of the universe that couldn't possibly have interacted with each other, and it's perfectly flat. So we want to understand how all of these things came to be. The natural question to ask is, what happened at the very beginning of the universe? We want to know what happened before all of the observations that came so far. So that is where the theory of inflation comes in. Inflation is a theory of what happened in the first fraction of a second of the universe's existence. So we talk about the cosmic microwave background being formed right near the beginning of the universe, but that was 400,000 years later. We're now going back to a fraction of a second, so it's a whole different ballgame. In brief, inflation just says that during this first fraction of a second of the universe, space itself expanded very, very quickly. The universe doubled in size and doubled in size again and again and again. And so at the end of inflation, you end up with a universe that is suddenly much bigger than the universe you started with. We're going back to our favorite blowing up a balloon analogy. This is like you have your beginning baby universe that's the surface of this small balloon, and then something causes it to expand super, super fast, and you end up with this much larger balloon here. This actually solves both the horizon and flatness problems. Getting back to what Stefan mentioned, how if you have two galaxies that are far enough apart, they seem to be moving apart faster than the speed of light, but they're not actually moving. It's the space in between them that expanded. This explains the horizon problem, because you have 2 points that were very, very close together and could interact with each other all they wanted to, and then suddenly the space between them just expands very quickly, and now they're much further apart. And so it may seem like if you were a light particle in one spot today and you set out to try to visit the other one, it would take you almost 30 billion years to get there. But when you were first at the beginning of the universe, the distance was nowhere near that long, and so you actually had plenty of time to talk to each other before space expanded and pushed you apart. It also solves the flatness problem, because it turns out if you allow the universe to expand this quickly, it will obviously end up looking much flatter, for the same reason that the Earth is curved, but it looks flat to us because it is very much bigger than our sense of scale. So you can it actually means that when the universe started before inflation, you could have a much wider range of possible degrees of curvature to it. It doesn't have to be as perfectly flat, because no matter how slightly curvy it might have been, inflation will go ahead and nicely flatten it out for us. And then finally, it also solves the problem of where did these perturbations come from, by relating it to known ways that physics behaves on very small scales. We like to say that during inflation, we don't know exactly what caused this exponential expansion, so what theorists do what they do best and came up with a new particle to explain it. It's creatively called the inflaton because it caused inflation. Hopefully you can all remember that. So you have these particles, and before inflation, they're crammed into a very tiny space. It turns out when particles when you're looking at how the universe interacts on very, very small scales, it's common for there to be these sort of random fluctuations. This is the scary field of physics called quantum mechanics. We won't go into it in detail, but it turns out that these small fluctuations on teeny tiny scales are a very well-known phenomenon. And then it takes inflation, and since inflation causes all of space to expand, these tiny fluctuations get blown up to the sizes that you see in the cosmic microwave background. So this question of where did the fluctuations on these scales that we can see in the cosmic microwave background come from, and why do they have this particular form, goes back to the physics that governs the very, very smallest scales before inflation. So any questions so far before I continue? Yeah. That is an ongoing area of current research. A lot of people are very excited about studying the very early universe because it offers this opportunity to unify theories that describe small scales very well and theories that describe large scales very well. Right now we have so the question was, does studying the large scale structure of the universe offer a promise for us to better understand how physics work on small scales? And the answer is that yes, this theory would imply it does, because that large scale structure is based on these tiny initial perturbations that are determined on the physics from small scales. So physicists really like to the idea of searching for a grand unified theory of everything that will explain both small scales and large scales. Right now we have these theories that work very well in the extremes, but we don't have one underlying equation that explains it all. And so people are hoping, yeah, that these kind of observations will allow us to do that.
What actually is flatness? How would you try to look at like a table or?
Yeah, so one way you can think of it is if you have a flat piece of paper, you go back to your middle school geometry, you draw a triangle on that piece of paper. You know that the angles of that triangle add up to 180 degrees. Now, if you draw a big triangle on the Earth, if you think about lines of latitude and longitude, you know that all longitude lines start at the North Pole and go down to the equator. And so when everyone hits the equator, it intersects it at a 90-degree angle. But you can also imagine you can make your angle between longitude lines at the North Pole anything you want. So you can actually have a triangle on the surface of the Earth whose angles add up to more than 180 degrees. So it's a little hard to visualize maybe without a figure to go along with it. Is that making sense? All right, well, I can talk to you more at the break. But yeah, the question was what does it mean for the universe to be flat versus curved? And the answer is, I was trying to get at, is one way we can determine whether the universe is flat or curved is trying to measure triangles on the sky and seeing whether their angles add up to 180 degrees or not. Another thing we can do is related to measuring this apparent size of these fluctuations on the cosmic microwave background. And based on their size and what we know about dark matter from other sources, it seems that the universe basically has to be flat. But I'll be happy to go into that more during the break. It's a little bit hard to explain without a visual. All right, I'm going to go ahead and move on. This is what I basically said on the previous slide, that we don't really know for sure what caused inflation. We have this particle called an inflaton, and inflation ended because when the universe got large enough, theorists say that this particle decayed into more familiar particles that form up the matter and light that we are familiar with. And I also wanted to draw an analogy with since we brought up this dark energy earlier, the universe is again expanding faster and faster. And this time, instead of an inflaton, it's dark energy. They are clearly similar phenomena, but it's unclear that they operate on different scales and they are different strengths. So they're related, but probably not the same thing. But it's good to note that there's still the universe expanding rapidly is not an unprecedented phenomenon. I just paused for questions. I guess I won't pause again here. Instead, we'll continue on to the next overarching question part of my talk, which is, okay, we now have this theory of inflation. You're probably not really believing me because it kind of sounds like I just made the whole thing up. So now the real question is, how do we prove it? So we like this theory. We want it to be true. It's our best idea for how to solve these three problems I talked about. But we want to have experimentally testable predictions. we want to be able to say inflation is great because it solves the problems we already thought of, but here's this new problem, and we want it to be able to, we want inflation to be able to make a prediction about the outcome of this observation we can make, and then we want to make the observation so we can see whether it's true or not. However, this is actually quite tricky because we're looking back, we're trying to figure out what happened at the very, very beginning of the universe, right after the Big Bang, less than 1 second after. And we need to do that with only being able to observe light from all the way over here at the cosmic microwave background. So we're trying to figure out what happened in the first second of the universe's existence, but we can only show up on the scene 400,000 years later. So we can't use light, which is the astronomer's favorite tool, to figure out what the universe looked like at inflation, at least not directly. So it turns out there's another kind of signal you can look for, and this is going to be our method of illuminating what happened way back here at the beginning of the universe. And these are called gravitational waves. They're basically, you can sort of think of them as like ripples that got set off when the universe expanded very suddenly. It's like when you throw a rock into a pool of water and there's these ripples that propagate outward. So space itself kind of gets squeezed and stretched, and these gravitational waves propagate out through the universe due to the sudden shock of inflation. And it turns out they actually leave a signal in the light of the cosmic microwave background that we can hope to detect. So this is a better picture of what a gravitational wave looks like. You basically have this wave, it's moving along the screen here from left to right. And as it moves, you can just kind of think of space as kind of squeezing back and forth like a slinky. It's sort of getting stretched out along this direction and squeezed along this direction, and it's just kind of going back and forth and back and forth. So when space gets squeezed in, all of the stuff that's in that part of space gets pushed a little closer together. When you compress a gas, you heat it up. So these parts right here get a little hotter, and these parts are getting stretched out, so they get a little colder. So you get this sort of characteristic hot and cold pattern as the wave moves by. Turns out this particular pattern is something we can look for. It makes a particular pattern in the polarization of the light in the cosmic microwave background. Now, I want to take a moment to explain what I mean when I say polarization of light. You may have heard of polarizing sunglasses, but it may not be clear exactly what's going on when you put on your polarized sunglasses and suddenly you can look out and see much less glare everywhere. So if you have a light source, light travels in waves, and so if the light's moving this way, those waves tend to oscillate in all directions. So if you polarize the light, what you're doing is you're only allowing one particular direction for light to go through. The analogy you can think of is, let's say you have a rope and you're holding a rope, and your rope extends through a picket fence. So there's vertical holes in the fence, and you decide to shake this rope in all directions. If you shake the rope up and down, there's no problem at all. The wave can continue to pass through because it can go up and down along the slit. But if you shake the wave side to side, the slit stops the wave from going through, so you can't get any of those side to side vibrations on this side of your fence. So it turns out that this particular pattern of stretching and squeezing space causes more light to be emitted from the hotter parts than the colder parts, and this particular pattern produces this particular polarization signature in the light from the cosmic microwave background. So this light was sitting in space, but the space is moving, oscillating a little bit, and so the light gets slightly polarized like this. So whenever the wave, the stretching and squeezing reaches a minimum point, you see less of this polarization signature, comes to a maximum, goes the other way. So as the wave travels through, you see this pattern that gets imprinted on the light as it passes through. Now, you don't just have one gravitational wave moving through the universe. Inflation happened everywhere, so you get waves moving in all directions. So what we really see when we look at the cosmic microwave background is we see a sum of all of these different waves that were moving in all these different directions. So if I just take that same pattern, polarization pattern from the previous slide, and then I have all these waves moving in different directions across here, and I add them all up, you end up getting this kind of swirly looking pattern here. So when we're looking at the cosmic microwave background, we want to measure the polarization of the light, measure which direction it's oscillating in. And if we look at the sky and we see these little swirly patterns, that's a hint that, hey, gravitational waves were probably here. So I'll stop again for questions. All right, keep going then. Hopefully this means you're with me and not, oh my God, that was way too confusing. So we now have said that these gravitational waves are proof that inflation happens. So if we can detect them, that's kind of a smoking gun. It tells us inflation is the way to go. We know how the universe began. We know this expansion happened. We know it generated these gravitational waves, and we see them. That's great. Now we have to do the hard part, which is actually going out and building a telescope that can measure the polarization of the microwave sky in precise enough detail that we can actually look for the swirly pattern, which is going to be very faint. So we need a really good telescope. We need a really great observing site. Anyone have any guesses what is the best place on Earth to go observe the sky and look for this cosmic microwave background radiation? Ah, you know the answer. So we actually go all the way to the South Pole to try to look for to measure the cosmic microwave background. I'm actually heading down there in about 2 weeks. We have a telescope down there right now and we're upgrading it. So I'm gonna go down and help with that. There are several different reasons the South Pole is a really great site to do this kind of astronomy. For one thing, it's in the middle of nowhere. There's no humans out there taking their microwaves out in the backyard, as Zach suggested, and trying to measure things. And there's also it's also a very dry place. You think the South Pole, you think snow, but it turns out it doesn't actually snow there. There's just a lot of cold, frozen water on the ground. So it's actually a very dry place. It's actually very high altitude. There's ice that goes down that's a mile or two thick before you hit the ground. So the elevation of the South Pole Station is actually about 10,000 feet. And we're very interested in looking at the cleanest part of the sky. Stefan showed you the beautiful photo with the Milky Way taking up a whole band of the sky. But the Milky Way has lots of stars and gas and dust in it. And the dust in particular can emit in the microwave. So we want to avoid the dust as much as possible, which means we really want to look at one part of the sky and we want to look at it forever. We just want to keep observing the same part of the sky until we can beat down our noise enough and see this tiny signal that may be lurking there. The South Pole is nice because, the way the Earth rotates, the same part of the sky is always above the horizon. So you can just pick a field and stare at it. So there's so my research group is not the only one that realized all these things make the South Pole a great place to do astronomy. There's actually a whole bunch of telescopes here. There is the cleverly named South Pole Telescope, which actually looks at galaxy clusters and microwave astronomy on smaller scales. There's my group's experiments, which are the BICEP series of experiments. We have BICEP 1 and BICEP 2, which just finished observing, and we're going to send a new telescope called BICEP 3 down this winter. Before you think we're completely uncreative when it comes to names, our current experiment that's down there now is the Keck array, so we are not completely wedded to this BICEP idea. So there's these two different buildings, and this is how you get there. They have a military grade plane that's fitted out with these special skis so you can land on the ice. It's pretty fun. And the telescope that I'm going to talk about is BICEP 2, which just wrapped up observing about 1.5 years ago. This is a picture of the telescope poking out of the top of the building, and it's just staring off at this part of the sky. And it observed for 3 years, stared at the cosmic microwave background, measured the polarization. And last March, we announced this very exciting result. For the first time, we detected B-mode polarization. The B-mode is what we call this sort of swirly pattern. So we detected it for the first time. We looked up at this patch of the sky. This is just the coordinates on the sky, and we see that there are places where the polarization does follow this sort of swirly pattern that you would expect from gravitational waves. Another way that we like to look at, another same way of looking at the same data is we like to look at the size of, the characteristic size of these these B-mode signals. So we want to look at, how far apart are the peaks, kind of the same way we were interested in the scale of the cosmic microwave background. So this is what in science we call the money plot. This is the plot that sums up all of our results. The x-axis is the inverse of scale on the sky. So things that have a higher number on the right side of the plot here are actually smaller things. These are bigger scales. And then this is just how strong the B mode signal is at those scales. So this is the BICEP2 result here. All of these other ones from previous experiments that observed the cosmic microwave background are all upper limits. This was as sensitive as the telescope was. So they couldn't actually get down to see the signal, which is down here. And this little dotted red line here is exactly what signal you would expect to see if these gravitational, or if this beam of polarization that we detected was due to gravitational waves. So you can see the data lies pretty much right on the line. So this is very, very exciting if we are hoping to tout this discovery of this signal as a sign that we saw gravitational waves. However, we're not completely rushing out and celebrating our victory yet. As I mentioned before, the dust in our own galaxy, although it can help us make really pretty images like this, is a problem. It turns out that the pesky dust in our galaxy can also emit microwaves in a way that produces a signal that is somewhat similar to the signal that that the gravitational waves do. The way you tell them apart is by observing the sky at many different frequencies, because it turns out that the signal from gravitational waves is about the same strength at all microwave frequencies, and the signal from dust tends to be more strong at bluer wavelengths. So if you observe at a high frequency, you'll see more dust than if you see it at a low frequency. So if you observe at multiple frequencies and you see that your signal gets really strong at high frequencies, you go, oh, well, my signal is probably mostly dust. But if you look at it and you go, huh, my signal is kind of constant, it's not really changing that much with frequency, then you go, well, maybe my signal is mostly due to these gravitational waves. So the initial results from BICEP2 were only at one frequency. We have our telescope that's down there now that's observing at another frequency, and results from that are going to be coming out soon. And we're also working with the team that made the beautiful map of the cosmic microwave background we've been showing throughout this talk, and they have data at other frequencies as well. So it's an exciting time. We're hard at work on the analysis right now, and more will be known as to whether this detection of polarization is in fact the first direct sign of what might have happened at the very beginning of our universe. So this sort of wraps up my portion of the talk. I told you about these gravitational waves and how there are a smoking gun for this inflationary theory, and how we have this incredible telescope that went out and detected a signal that looks like it could be due to these gravitational waves, but we're still working on the interpretation of it. And if it's right, it's a very significant result. If not, we may have to wait a little longer for technology to continue to advance. And at that point, we will hopefully be able to learn something about the very beginning of our universe. We're continuing to push the frontiers. So this ongoing work, now we have come all the way from the Greeks at the very beginning of our, who understood the night sky by looking up at the stars and didn't know about separate galaxies, all the way to now, in modern times, we can push all the way back to learning about the very, very beginning of the universe. So we have this beautiful model where we started out in a very chaotic state, and then there are these tiny perturbations that were generated due to inflation. Then these perturbations grew over time as gravity overwhelmed pressure and the expansion of the universe trying to pull the perturbations apart. And then eventually those perturbations grew into the galaxies and galaxy clusters that we see today that make up our ordered cosmos. And it is very beautiful, and we will continue to learn more about it as time progresses, and we're just very lucky to be able to know as much as we do. Thanks. So I'll now take questions, and Zach and Stefan will also be around afterward to take questions as well. We have various pieces of modern astrophysical equipment, I believe is what it says in your handout, These, so I have one of the lenses from our telescope that was used to make these measurements to the CMB, and we have various cold weather gear you need to work at the South Pole, and we also have one of the plates from the telescope that was used to make this lone digital sky survey. So if you're interested, stick around. I'll be there about 6 weeks. And I mentioned we have a telescope down there now called the Keck Array, which is working on observing at a second frequency from the one that BICEP 2 reported. Now that there's a lot of concern about dust, we want to observe at more frequencies because more is better. So we're upgrading the telescope to observe at a third frequency. So I'm going to be going down and helping take the telescope apart and put the new detectors in that can see this new frequency and put it back in and get it working again. So the question is getting back to the flatness of the universe. It's I use the two-dimensional analog because that's easier to visualize. It's very hard to visualize what flat or curved three-dimensional space looks like without invoking higher dimensions. So yeah, the easiest way to visualize it is to imagine that we live in a two-dimensional universe, and our universe could either be a flat piece of paper or a globe like the Earth, and we can measure shapes on the sky to try to figure out which one it is. In the back.
I was having a problem with the last also, and I was, isn't it the fact that you look every direction, it seems to be green,
so the question was, is flatness related to looking in the universe and seeing the same thing in every direction? And the answer is that's a separate problem. That's what I called the horizon problem before. So that's actually not related to flatness. They're two separate issues. The first issue is how can things that are so far apart possibly have interacted with each other in the past? And the second is why does the universe appear to look like a flat sheet of paper as opposed to a globe or a potato chip or some other shape you could come up with? Yeah.
But we also talked about that there is still ongoing expansion.
Yes.
Are these related, and if they're not, how are they different?
So the question is, how is the current expansion of the universe due to dark energy related to the expansion that happened during inflation, if they are related? The answer is that if you work out how much outward pressure the inflaton would have to have exerted on the universe to cause that expansion versus how much pressure the dark energy has to exert on the universe, the relative strength of these two things are quite different. Inflation happened very, very fast, and the expansion that's happening now is a longer ongoing process. So they do seem to be similar kinds of phenomena, and that they're both periods where some force or some element in the universe was pushing everything else away from it very quickly. But they are probably not the same thing just because the time scales and the strength of the effect is so different. Way in the back. So the question is, what happened to the idea of the universe having a hyperbolic shape? That is also currently ruled out by observations of the cosmic microwave background and the large scale structure, which show that the universe has to be flat. I didn't really mention the possibility that the universe could be hyperbolic in shape because that's a little bit harder to visualize. But yeah, astronomers initially were wondering, it turns out if you have a perfectly flat universe, you can't, or if you have a perfectly empty universe with basically nothing in it, it's hard to explain how it could be flat. And a perfectly empty universe would end up looking more like a potato chip than a globe or a flat surface. So yeah, the answer is that current observations basically rule it out. But it's a nice, simple model if you're starting to learn about these things. No, no, it doesn't. Space is allowed to expand as long as nothing within space is moving faster than the speed of light. Einstein basically added another term in his equation that was a constant term. And he actually at one point called it his biggest blunder because he initially added this term to explain why the universe wasn't expanding. This is what Zach was getting back to. When Einstein first came up with his theory, everyone didn't know the universe was expanding. They thought it was just kind of constant and it had always been. And Einstein developed his theory and said, I really need a universe that expands or contracts. So he just added a constant to make it so that the universe was steady. But it turns out if you make this constant a little bigger, you'll get a universe that expands faster and faster. So people do sometimes call dark energy the cosmological constant. And it looks like it is not zero after all, much to Einstein's sadness. Yeah, you had a question. It's a good question. So the question is, does the chemistry of the atmosphere influence why the South Pole is a good site to do microwave astronomy? Really the biggest thing about atmospheric chemistry that helps us is the fact that there's very little water vapor in the air. It turns out that water really is very good at absorbing incoming microwaves. So if you want to see the CMB, you really like to do it on very dry days. That has a lot more of an impact than the ozone hole coming and going because those ozone particles interact with microwaves less. In the front, yeah.
The Earth's electromagnetic field, doesn't that kind of loop around both poles without affecting your thing? Doesn't that be?
Yeah, so that's another good question. The question was, does the Earth's magnetic field impact our measurements? And the answer is that no, it does not. You can actually, take pictures and see the aurora, but that's all visible light, so it's not going to impact our observations of microwave light. And the incoming light isn't deflected by the magnetic field of the Earth. So the fact that that we're near the magnetic pole doesn't really make a difference for our observations. I'll take one more question. Yeah. Yeah, so the question is it easier to look for inflation with ground-based experiments or satellites? The advantages of a satellite are that you can look at more of the sky, and that is what the Planck team has done. They've launched this wonderful satellite that took data for years and years. But the downside to satellite observations is that they're really expensive. And it's actually a lot cheaper to go to the South Pole than it is to launch a satellite into orbit. And it turns out that the scale, like the characteristic scale of the polarization signature from gravitational waves is small enough that you don't need to observe the whole sky to see it. And since a lot of the sky is obscured by the dust in our own galaxy anyway, we really just need to pick our strategy was to pick a small patch of the sky. And since you don't need to see the whole sky, there's less motivation to go all the way to space, which is very expensive. But since we do have this lovely data from the satellite in space, it's really complementary. And so we can combine the data and get the best possible outcome. All right. Thank you all for coming. And we'll be up here if you want to come see our equipment.